in other words, they lack symmetry. By the same token, anything that is superimposable with its mirror image is achiral. Or symmetric. So when we say symmetry, you can either look for a center of symmetry or a plane of symmetry. In either case, that would be, as long as one part of the molecule is mirror image of the other part, that would be symmetric molecule, and therefore that would be essentially achiral. That would be achiral. So let's look at this too. As I mentioned, if you change one of them to the same atom or group, then they will become achiral. Because one part of the molecule will become mirror image of the other part. And let's just show that. This one is chiral because it has no symmetry element. But if you make two of the groups or atoms identical, as in this case the green ones, then there is a symmetry element. Okay, the symmetry is, where is the symmetry? You can consider a plane of symmetry going right through the middle of this, and then one part is the mirror image of the other part, and therefore that makes it symmetric, and therefore this molecule will be achiral. And the same way, you can consider many other molecules and figure out the symmetry elements. For example, if you have a right-hand glove that is non-superimposable with your left-hand glove. Therefore, that is also chiral. On the other hand, if you consider a basketball or soccer ball, that is going to have symmetry, because if you cut it right in the middle, and one part is the mirror image of the other part, so therefore, like the baseball bat also is. Okay, that's a symmetric object. So we use these concepts to understand these issues. Now, why do we do that? Because if we have two molecules that are mirror image structure but non-superimposable, then they have certain other properties. Okay. So let's assume that you have, as we start with 2-butanol, 2-butanol we can have two different structures of that. So if I write the structure of 2-butanol, the 2-butanol can be written as two different structures, where this is the chiral carbon. Why? Because there are actually 4 carbons, but this one has 3 hydrogens. As I said, if you have 2 atoms or 2 molecules that are attached to them are the same, then they cannot be chiral. So this one is not a chiral center. CH2 also have 2 hydrogens, therefore that cannot be chiral center. This is CH3, that cannot be chiral center. The only one that has 4 different atoms and groups attached is this carbon, and therefore that is the chiral center. And then we can write that as follows, that we can write approximately 109-degree angle, 2 of the groups, doesn't matter which one. You have OH, and then let's say CH2, CH3, and then we write the others as OH and dash. Therefore, that would be, let's say, methyl and the hydrogen. So that is non-superimposable with this mirror image structure, which is on the other hand would be OH and then CH2, CH3, CH3, and then H. So then there are two different types of 2D rocks are there. Now, when we look at their properties, their chemical and physical properties are almost identical, with the exception of one. Okay, and typically, when we have, these are of course, as I mentioned before, the term we use is these two are enantiomers. So the enantiomers have most of their properties are identical, okay, except one. And of course, their biological properties are very, very different. In most cases, enantiomers have very different biological properties. Why? Because enantiomers, because of their three-dimensional orientation, often react with biological molecules very differently, because enzymes and others have active pockets which are very defined, and one may fit in that, another may not, and therefore they will exhibit completely different properties because of that. And as a result, we see, for example, we have very common biological molecules like cholesterol and other properties. They have a plus and a minus enantiomers, and those enantiomers will have very different biological properties, even though their chemical properties are nearly the same. All right, now one particular property that is often used for distinguishing them is the optical property. Before I get to the optical property, let me explain how we measure that. Okay. So let's assume that you have a source of light. A light typically goes in every possible direction, right? This is a source of light. Because light, as we know, as wave properties, they will have wavelength. Typically, this is the way they go, and of course, their wavelength and the amplitudes will be different depending on the various factors. But they go virtually in all directions. Right? However, if you pass them through a prism, they can be plane polarized. Often we use a polarimeter, but originally it was started with the prisms. So you pass this light through a polarimeter. And that makes the light plane polarized. Let's assume this is going in this direction. Plane polarized means that rather than going in every single direction, it's going in one particular plane. The waves are going in one particular plane, and that is therefore called a plane polarized light. Now the plane polarized light, if we use this light through a sample chamber containing, let's say, your compound. So this is a sample chamber. And the light may have two different consequences. One would be that it would be exactly like the same way. then we'll call this compound optically inactive. And if, however, this changes the plane polarized light in any particular direction, so let's assume that after going through the chamber, the plane polarized light is now moved to a certain angle. So original angle was this, so this would be, let's say, alpha is the angle. Then we'll call this compound that was used in the sample is optically active. So this compound now is optically active. And now, because you can change the optical activity using different concentration of the solution, different length of the tube through which this is passed, therefore we need to standardize them. And typically, standardized method indicates this alpha to be recorded as follows, so that we can do the experiment under the same set condition. Alpha is shown within the bracket like this. On the bottom, we indicate what kind of light was used. And typically, we use D. The D stands for D line of sodium. D line of sodium has a specific wavelength, which is 589 nanometers. And then on the top, we indicate the temperature at which it was measured. And the temperature is typically most frequently rise 25, which is the room temperature. So now, what is the relationship of the observed rotation here, which is alpha? It's given as 100 alpha divided by CL. Okay, C is the concentration of the sample of the compound in grams per 100 milliliter. And L is the length of the tube, sample tube. Length is used in terms of decimeter, DL. And that gives you the alpha D value, which is commonly you can compare with that. Now, for 2-butanol, in fact, there are this is 13.1. So, based on that, we can report the optical activity of each compound. Right? Now, it can rotate in the positive direction, clockwise, or counterclockwise. That direction essentially gives you that number. So, the way we report it is, for example, let's say lactic acid has approximately 3.8. So one enantiomer of lactic acid gives you the rotation of plus 3.8. And therefore the other enantiomer will give you minus 3.8. Exactly equal and opposite. And obviously if you mix equal amount of the two enantiomers of lactic acid, then the net would be 0. Right? So that we call, even though each individual molecule is chiral, the mixture itself is achiral, and that we call a racemic mixture. Equal amount of both enantiomers. present in the mixture. Right, equal amount is present, and therefore it becomes optically inactive, even though individually they are both optically active. In fact, to give you an example of that, okay, you know the anti-allergy drug that some people use, Zyrtec, that is actually a racemic mixture that is being sold. And like the dosage that they give you is 10 milligrams for each dosage. Now, the more advanced version of Zyrtec, which is called levocetirizine, is the one enantiomer that is active. And that one, now they give you, it's a different commercial name, I don't remember that. But that new drug is essentially gives you a pure material, and you need half of that. You need 5 milligrams for that dose. So that's because they don't need the whole amount, because it's a mixture and there's an inactive component in there. Okay, so there are many, many examples of that, particularly in the drug industry is very common. One enantiomer is very active, the other enantiomer can have even a bad effect for that matter. It's very common. Okay, so racemic mixture is therefore equal amount of both enantiomers. Now, another term that we use is enantiomeric excess. Or EE%. What that term means is that sometimes you may not be exactly equal amount, but you have a mixture where both enantiomers are present, but the amounts are not equal. So let's assume that you have one enantiomer presenting 25%. Let's say the plus is present at 25%, and the minus is present 75% in the mixture. In that case, we'll call this is minus enantiomer is 50% enantiomeric excess. Is present in 50% excess. And do that by essentially subtraction, because 25% of this would be neutralized by the 25% plus enantiomer present, and therefore there will be 50% excess. And accordingly, let's assume that the rotation is standing plus 10 degree here, and minus 10 degree here. Therefore, what is going to happen that the net will give you essentially a minus 5 degree, right? Because 25% of this is neutralized by the other 25% of loss isomer, and then you end up getting a different reduced net minus 5 degree. And so this is a fairly simple calculation to see how the enantiomeric excess are calculated. Absolute and relative configuration. Now, most of the time, the optical property, as I mentioned, that's an experimental property. You get pure isomer, pure enantiomer, and then you can measure that and figure out what the optical activity is. However, how do I correlate with the structure? Because, for example, in 2-butanol, we have two structures we already have drawn. But which one is the plus isomer, which one is the minus enantiomer? Okay. the only way to do that is by extracrystallography, which was not actually was done, or this technology did not develop at the time the first enantiomers were figured out. So how was it done? At that time, it was taken arbitrarily, one enantiomer, and then everything was related to that. So if you do a reaction and change a molecule, but not involving the chiral carbon, then the product that you are getting from that would also be related to the first compound. So if it was first plus isomer, the product should be expected to be plus isomer as well. So let's assume a reaction where, let's say, in this case, this is the chiral carbon, because it's attached with 4 different groups, 1 hydrogen and ethyl, and the CH2OH. Now, if you change this molecule, and let's say you have a specific enantiomer, plus enantiomer. If you change this molecule by a reaction such as the HCl to the corresponding chloride, then you get also a different chiral carbon, but the chiral carbon was not affected. So the stereochemistry would remain intact, and you expect to get, even though you don't know exactly, but you can say this is also going to be a plus isomer, because it started with a plus isomer. So that's essentially the relative configuration. Yes. No, I didn't say it's not. This is, yes, but this is essentially, it protonates the oxygen, and then the chlorine, because it's a primary, it cannot be, cannot leave the carbon atom, so the Cl will attack and displace that. So, but the reaction, the important thing to remember is that the reaction does not involve the chiral carbon. So the chiral carbon doesn't undergo any changes. The change is happening on this carbon, which is unimportant for determining the configuration of the molecule, or the 3-dimensional architecture of the molecule. And that's what the relative configuration means. I'll go through that again on, what is that, Friday. And go through this concept again. And this time again, you have to use the in order to figure out what we are talking about, you have to figure out the 3-dimensional architecture or the models for doing this. And let me give you an example. One of the ways we can determine that, as we mentioned, that how do we, rather than drawing the structure, how can I figure out which one is which? So there is a nomenclature method used, and that is called the Kahn-Ingold-Prelog system, where, if you remember, we previously used for higher or lower on the carbon-carbon double bond, the Kahn-Ingold-Prelog priority rules. Okay. And the same rules apply here. Now what we do, we take one of these, let's say that we rewrite this. So we have this OH. So in terms of the priority rule, we can rank order them. And by rank ordering, we have to put the oxygen at that number 1. Right? So this is 1. The second is there are 2 carbon units. This one can be written as C connected to CHH. And this one is HHH. therefore this has a higher priority. So this is number 2, and this is number 3, hydrogen is 4. Once we assign the priority rule, then the number 4 group, you need to tilt it so that it goes in the back. So in other words, let's say this is the hydrogen. So you tilt it in the back so that everything from your point of view comes up as like a triangle. And in this triangle, let's assume this is the OH, right? And then we have CH to CH3 is green, and this blue is the methyl group, which you go from 1 to 2 to 3. That would be from your direction, it would be clockwise. Right? And then clockwise direction of this group can be indicated. So this one we rewrite that. And the hydrogen goes in the back, therefore so this is a clockwise, and we call it up designation. And if it is counterclockwise direction, which will happen with the other enantiomer, which is this one, and we can directly do it here. That hydrogen is already in the back. So this is 1 to 2 to 3. This is counterclockwise, right? And therefore this is S enantiomer. So R and S nomenclature essentially figures out which enantiomer you have, and you can write the structure in many different ways. You have to follow the rule that 1 to 2 to 3, putting the 4th group in the back, should go clockwise or counterclockwise, and that will tell you R or S nomenclature. Okay. And we'll go through some of those examples. Now, we also need to worry about symmetry or asymmetry. So there are many different types of molecules that you'll be looking at. And in this case, I have given examples of 2. In one case, you have a plane of symmetry right through the middle of this. Okay, not through the middle, sorry. But this one has 2 groups identical. And so you'll be able to find a symmetry property from this one. Because these 2 are exactly identical, so this is achiral. Whereas this one has completely different groups attached to the carbon, so this is a chiral molecule. So there are some examples that you should go through and just figure out that you have a clear concept of chirality as well as the symmetry properties of the molecules, right? Okay, let's go through the practice, please. Yes? Yeah, the mini exam is just similar to the handout that I gave you, the practice quiz, which has only 2 or 3 questions on chirality, and all the others are essentially from chapter 6. Okay, so the first question is, what is the product in the palladium caramelized hydrogenation of 1,2-dimethyl cyclopentene? So you start by drawing the structure, 1,2-dimethyl cyclopentene. Okay, and here you have a methyl group and methyl group. Now, the mechanism of the reaction is, on the metal surface, both hydrogen come from the same side. So this is a seam attachment of both hydrogen. which means they would come from the same side, and therefore both metals would go in the same side as well. So the answer is cis-1 2-dimethyl cyclopentane. Which alkene below is thermodynamically the most stable? 1-hexene, let's draw the structure. 2, 3, 4, 5, 6. 1-hexene, trans 3-hexene. 2, 3. So this is trans 3-hexene, and cis would be this. Okay, the hydrogens are on the other side. Okay, and 2-methyl 2-pentene. 2-methyl. So the main difference between them is that this is monosubstituted with the alkyl group. These two are disubstituted, right? And this one is trisubstituted. 3 substitutions across the round. And therefore, this is going to be the most stable, right? So this is answer is B. The stereochemical pathway for the hydrogenation of an alkene with a metal catalyst such as platinum occurs via scene addition, which we already mentioned. What is the major product of the following reaction? And let's follow the reaction. That is the best way to approach this. This is going to follow the Markovnikov's rule. So the hydrogen will be added on to the carbon, which has one hydrogen, the other carbon has no hydrogen. So this would be where the hydrogen would add on. We'll generate a carbocation here, and then bromine would add on to that one. Which is 2. Okay, which of the following is not a possible reaction of a carbocation? Addition of a nucleophile, okay, that is of course a reaction of the carbocation. The arrangement to a more stable carbocation, that is also common, no. Addition of a proton to form an alkane, you cannot do that, right? So this is wrong. Loss of beta hydrogen to form an alkene, that is correct. So C is that. Addition of HCl to 3-methyl 1-pentene gives 2 products. One of these is 2-chloro 3-methyl pentane. What is the other product? Okay, so let's start with 3-methyl 1-pentene. 1, 2, 3, 4, 5. 3-methyl 1-pentene, right? And so if this one is treated with HCl, the first step is addition of the hydrogen according to Markovnikov rule, right? So H plus is added, and it will be added at the end. Then this generates a carbocation. Now, this cation can go to the product, which is really the product that they are talking about, 2-chloro 3-methyl. So the chlorine can attack this and form the 2-chloro 3-methyl pentane. But it can also undergo a carbocation rearrangement. So ideally it would take a hydride transfer and make a very stable cation. This is secondary, it is going to generate a tertiary cation. this cation would be generated, and therefore that would be reacted with chlorine, it would be the other product, generating Cl, which is therefore 3-chloro-3-methylpentane. Which reagents below would work best in converting 2-methyl-2-hexene to 2-methyl-3-hexanol? So 2, 4, 5, 6, 2-methyl and 2-hexene. 2-methyl hexanol. So you need to add the OH here. And because if you do the 50% sulfuric acid reaction, the hydrogen is going to add on to this carbon. This is really an anti-Markovnikov product. And therefore the ideal one would be the diborane reaction that will carry out this. The hydroboration oxidation reaction can be characterized as the anti-Markovnikov syn addition of water with alkene. What is the major product of the following reaction? And this one again, you are adding bromine. And so it would be this product where 2CH2CHBr, and then the other one is CBr, CH3, CH3. So these are the two bromines where it would go, and therefore 2,3-dibromo-2-methylhexane would be the product. Each of the following series of reactions would convert cyclohexanol to 1,2-epoxy cyclohexene. That's the epoxy. And the only reaction that we learned so far is that it could convert a carbon-carbon double bond to an epoxide using a peroxide acid. So the intermediate that you want to get here is a double bond here. And that can be converted to this. And therefore the ideal method would be using sulfuric acid with heat, and then you have peroxy acid present that is going to carry out the second reaction. So it's two-stage process, which is C. Which of the following gives acetone? Acetone is CH3CH3CO. So this is acetone. And in order to get that, you have the carbon-carbon double bond here that needs to be broken. And the only one that has that is this one. We can break the one here, which would form a carbonyl here, another carbonyl here. So the answer is D. Which of the following groups has the highest rank as assigned by Kahn-Ingold-Krylov system for stereogenetic carbons? And again, the first point of difference where you do it, and you can rewrite all of them, but fairly easy to do. You have C, C, H for the first one. Second one is O, H, H. Third one is O, O, H. When you have double bond, you count it twice. And CH2SH is C, S, H, H. And because sulfur trumps everything else, this will be the one. Okay, to each point on the potential energy diagram corresponds to hydrogen chlorides. And so 2-methylpropene is CH3 CH2. Right? So you are using HCl. So the very first step is converting this to the corresponding carbocation. So the carbocation that is generated is this. This is what is formed, right? And during this process, therefore, you have the partial bond between the carbon and the hydrogen is formed. Partial bond of the double bond is broken, and the positive charge partially migrates to carbon, and the chlorine has partial negative charge, right? Because it's breaking the bond between H and Cl. So that's exactly the transition state between these two will form, and therefore that is actually B. This is the structure of B that is indicated, and C is the carbocation that is I wrote here. So these, which of the following molecules below are chiral? And again, we look at chronosymmetry properties, and this is of course symmetrical completely, and therefore A and C are asymmetric. C actually has two different chiral centers, but A and C is this. All right, so the last one, give the configuration respectively of the following two molecules. Again, R and S nomenclature, as we have indicated, it's very easy to use a model where you can mark them red, blue, green, whatever, and then figure it out clockwise or counterclockwise rotation. But here we can also do it without doing that. If we rewrite this, putting the lowest priority, priority is 1 is bromine, 2 is chlorine, and methyl is 3, hydrogen is 4. So we gotta look at the molecules so that hydrogen goes in the back. So I have to put my eye over here in order to see it. And so that puts the methyl on the top, the bromine on the right, and chlorine in the left. Right? Because the chlorine is on the bottom and the bromine is sticking up. Therefore, we gotta look from this side and see what that they look like. And that would be Br2Cl2. So this is the R isomer because it's clockwise. The second one is again, this is 1, this is 2, and this is 3. In this case, if the hydrogen is up front, you have to look from the other side. And again, we can see that the way it would look like is that if this is from this side, it's 1 to 2 to 3. Looks like a clockwise, which is from the other side, it will be counterclockwise. It's 1, 2, 2, 3. If you look from the other side, you have to imagine taking your eyes in the back, so that the hydrogen goes in the back. That's the only way you can do it, right? So this is R and S. Again, these are very easy to do if you use models.